Welcome to Data Science 101, where we discuss the topics of the day surrounding data science, machine learning, AI, and deep learning. I'm your host, Daniel Gutierrez, and I am a data scientist, a educator, and book author, and I do a lot of writing about this whole area. So let's get started today with a sort of an inaugural topic for this series where we'll talk about the data science process. Now, this is the process that data scientists use to engage in pretty much any project surrounding the field of data science. And we'll be talking about this process via the slide that you see on the screen, which is composed of a number of rectangular boxes representing the different stages of the data science process. So the way this works is we start off at the left and we move incrementally towards the right in stages. And as indicated at the just below the boxes are the arrows that point both ways. And what that means is, although our desire is to keep moving from left to right, on occasion we get to a stage in the data science process where the results maybe aren't as we had hoped. And so we're urged to maybe take a step or more, maybe a few steps backwards, in order to further set the stage for moving forward. So let's start at the leftmost box, which is titled Define the Problem. Now, this is arguably maybe the most important stage of the process, because it's so important for us to define the project as a whole, specifically defining specific business goals. What I find in my own data science practice is often the client or the project stakeholder will be very motivated to just start the project and start coding and start doing machine learning, but that's not always the wisest approach. It's often better to sit back and really contemplate what the business goals for the project are. So in this stage, what I do is I typically will have discussions with the project stakeholders to see exactly what they hope to achieve with the project. What goals in the business are they seeking to achieve? And I'm often surprised at how maybe little that the people who are paying for the project have really sat down and thought about what they hope to achieve, and that is sort of a early recipe for disaster of the project if you don't sort of think about these things up front. It may turn out that a data science and or machine learning solution to their problem isn't the best choice. It could be maybe a data analytics or even maybe an Excel solution could be the path of least resistance. And I'm very upfront in telling people that maybe they don't need data science to solve this problem. So the way I usually do this is I cut off an early stage of my projects. I call them a discovery phase. And so with this, I interview different people involved with the project and get their perspectives on what they how they look at the project. And I try to come to a consensus so that um, we can all agree what the project is to entail. And so I will actually write a brief report that I deliver to the client for them to sign off on. And that's important because if they sign off on the description of the project, commit their resources and their money to the project, that means that they've thought about the project to a significant degree. Um, so part of that process too, the discovery phase, is also determining whether there is actually data available for a data science solution to the project. Often I have found that people believe they have the data, but when I, engage maybe an IT person or a departmental level person to explore the data sources, lo and behold, the data doesn't really exist in a form that I can use for solving the problem with data science. So it's pretty important to lay all these things out early on in the project so everybody knows what's going on. And the other thing is to classify the project as either a traditional machine learning project involving prediction, or is it more of a knowledge discovery project? So are we going to be using supervised machine learning or unsupervised techniques? That's important to decide up front. So let's say, uh, we do the discovery phase, we get the sign off on the project, and everybody's happy at that time. We move forward to the next box, which is data access. So data access, of course, it's foundation to any data science project, and that's where we determine our data sources. Um, where does the data live? I mean, maybe it lives in more than one place, and so we have to determine methods for collecting the data. The method of access, is it going to be the kind of thing where um, maybe an IT department will uh, produce an extract for using with the project, or is it something that maybe we have direct access to an internal enterprise SQL database, or are they, external data sources? Do we have to go to a data broker, data provider, access the data through APIs, or do we, or maybe the data source is something like social media, where it's just sort of out there in the ether, and we have to determine how to gain access to the data set. So that's important when discussing data access, and then also we have to worry about what format the data is in. Is it something like something simple like CSV? Is it something simple like Excel? Is it like I said? Is it in a SQL database? I mean, is it JSON? I mean, what are we going to work with? We need to know the format of the data, so we'll have um, uh, libraries or packages in our coding language to be able to access the data. We have to also worry at this stage about the quality of the data. The quality of the data is instrumental to the success of a data science project, because if you have data sources, that's great. But if the data itself is of poor quality, then we have to worry about how to improve the quality. Is the data full of missing values? Is the data inconsistent? Uh, there's or is it in a format that's easily accessed? Is it tabular data, for example? That'd be great. Is it non-tabular data and not so great? So we have to worry about things like this. Well, I mentioned missing values because you have to decide maybe up front what you're going to do with those missing values. If the missing values constitute a large proportion of the data, then you have to worry about methods of imputing the data, for example, or other methods. So we do have to worry about that. Now, one thing which will be great at this stage, data access stage, is if the sources of the data have an associated data dictionary. And that means, is there a document someplace which describes the data set in detail? What is, describing the data, describing each variable, what the variables contain. Um, you know, there's a lot that can be uh, put into a data dictionary that will really help the data scientist move forward out of this stage. So let's say we've gained access to the data and we're now ready to proceed further. The next stage is transforming the data from its raw form into a processed form that we can move on towards a machine learning solution. So this stage has a number of names: data munging, data transformation, data wrangling. These are all terms that are used to describe the process of taking raw data and converting it to processed data. So things like, I mean, there's so many things you can do with respect to data transformation. It's really a function of what the raw data looks like and how many steps are involved in order to transform it into a form ready for machine learning. And transforming it, well, the end result of that transformation, it really needs to just be a tabular data set. Rows and columns of data. So things you might have to worry about, again, with respect to missing values, to resolve the missing values in a number of ways, maybe imputing the value, maybe just removing the values if that makes sense. You also have to worry about transforming date and time data. So when you import date and time data into a coding language like R or Python, the data is not in a form that you can use as date as time data. It's usually imported as maybe a long integer or maybe a character string. And while that, those data types are temporarily sufficient in order to import the data, ultimately they're not going to be very useful if you need to do some sort of calculation on the dates and or the times. So you have to worry about getting the date time data into the right object class. You might have actually have to worry about normalizing data values too. So if your continuous values, numeric values, are vastly different magnitudes, then depending on the machine learning algorithm that you decide to use, you may need to scale the numeric values so that they're not so widely divergent in terms of magnitude. So there's language features that you can use for normalization process. But the goal that you're sort of looking at here in the data transformation step is to fill your feature vector. And that means is to choose your predictors that you feel will be useful for the machine learning algorithm that you choose and you will use later on. And so that is sort of the output of this stage. And that's very important, obviously, because you need to know early on where your predictive variables are going to come from. And I mean, it might be simple if you have a relatively small data set, but if your data set has hundreds of variables, then it may not be clear what that feature vector will contain. So you're on the lookout uh, when you're doing data transformations for the purpose of filling that feature vector. And one thing I should mention here also is that data transformation may involve many, many steps in transforming the raw data to processed data. And all those steps need to be collected together in what's called a data pipeline. So the data pipeline is something that you don't run just once. You reuse the data pipeline because typically in a data science project, once it's done, you want to periodically refresh the data, the original data. You might want to go to the original data sources and read them again. Presumably there'll be new and better data that's available. So you basically have all these steps collected as a data pipeline, and you can rerun it and come up with the processed data once again. So you might run the pipeline every quarter, every year, whatever makes sense. So that pipeline code is very important to the project ultimately because it is reusable. Okay, so next step is EDA, or exploratory data analysis. Now, these boxes right here that I just looked at transformation, I'm looking at EDA now, and also data visualization. They're separate in this data science process diagram, but really you do these sort of concurrently. You transform the data, you explore the data, and you visualize the data sort of all at the same time. So you may be skipping around in these three boxes here, depending on your motivations for looking at the data in different ways. So here we're exploring the data numerically. So we're using things like statistical functions, for example, to analyze the data. You might also use SQL to analyze the data, to retrieve and maybe aggregate the data, count data, sort data, whatever, to get deeper understanding of the data that you're using. So maybe hypothesis testing is another thing you might want to do while exploring the data. Maybe you're looking at probability distributions that might map to the data that you're using, so you can gain better understanding of the data by knowing more about the probability distributions that it might align with. This is also an area where you should be cognizant of outliers. Okay, so when you're exploring the data, undoubtedly you will notice any outliers in the data. Now, outliers, that's kind of a subjective thing, a subjective discovery, in the sense that you don't know whether the outliers are really good data or whether they're improper data, maybe errors in recording or errors in measurement or something like that. And so sometimes you need to get advice about how to treat outliers. And the way you get advice is to talk to a subject matter expert that hopefully will be available to you, so you can drill down with them, show them what the outliers look like, and get them to tell you, yeah, that's perfectly reasonable. We've seen that before, or no, that's a complete surprise, and the outliers shouldn't be there, or they're the result of some sort of error. So that's important to get settled at this point. The next box is data visualization, and here we're still exploring data, but we're doing it visually. So visually is very important, because even though with EDA you might get insights by looking at the numerical results of statistical functions. For example, with data viz, you can often find out things that about the data that you could never really discern with just numeric only exploration. So with data visualization, you're primarily generating two types of plots: exploratory plots and expository plots. So exploratory is where you're just thinking of all sorts of ways of visualizing the data, and you're just generating a lot of different plots, most of which will not be very helpful in your understanding of the data. And that's fine. You can generate like tens or hundreds even of these plots in your exploration. But you only keep probably a small minority of the plots that you generate. And those ultimately become your expository plots, which are maybe probably more detailed, more dense, more components, and you probably take more effort in making expository plots look nice and maybe presentable to maybe a non-technical audience. And these expository plots, by the way, would ultimately become part of your end product, and that is whatever sort of report you might write that summarizes the effects of the project. This is when you would do what I call data storytelling, and that's why these expository plots are very important to come up with. So expository plots, much fewer number of those than the exploratory plots. Let's see then. Okay, so if everything is good at this point, we've got a very deep understanding of the data, which means we will be led to a fairly confident list of feature variables. And so now we have these predictors. And oh, I should also mention, of course, that you decided what response variable you want to use. That is, what are you trying to predict? Is it a continuous response variable, in which case you'll probably be using a regression method, or is it a categorical variable, in which case you'll be using a classification method. And so at this stage is when you decide what machine learning algorithm that you wish to use for making predictions. And at this stage, you will also have a tabular data set, probably like a data frame, that you can then pass as an argument to a machine learning algorithm. You configure the algorithm. You select different hyperparameters that you feel are appropriate for the solution, and then you let it rip. You train the algorithm. You split the data set into training and test. You train the algorithm. You try using the test set to see how predictive the results will be for your intended goals, and you see where you go. You see where you go. Now, it could be that you get all this way and you're really not doing prediction at all. You're just looking for knowledge discovery. So instead of engaging a regression or classification algorithm, maybe you're going to be doing some sort of unsupervised machine learning, and you're doing some like a k-means clustering or a hierarchical clustering algorithm to gain insight into the knowledge you're trying to extract. So nevertheless, after this stage, you're looking to evaluate the model. How well did your algorithm achieve your goals? So you can have certainly numeric metrics. You like for regression, you might look at a root mean squared error metric, an R squared. Maybe for classification, you're looking at some ROC curves. You're maybe looking at a misclassification error rate to help you determine what's going on. So numeric metrics is one way. You also have diagnostic plots. So pretty much every machine learning algorithm will have its own complement of diagnostic plots that you can have the algorithm produce, and then you can analyze and determine what's going on and how good the algorithm is performing. I mean, things like overfitting is something that you would discover at this stage. Overfitting is not a good thing, and you have to. That was one of the things I was alluding to in the very beginning of this session is to, if you find that your results are not satisfying your goals, then you have to backtrack at this stage. You might have to maybe tune your algorithm in a different way. You might have to go all the way back to data munging and do different transformations. And God forbid, you might even have to go back to data access and find maybe different or supplemental data to cure the problem that you've discovered just now. Okay, so being a data scientist and engaging in the data science process means a lot of back and forth with this process. It's very rare that you will go straight through and achieve great results right off the bat. It's just not often something that happens. And so let's say though, after maybe a number of iterations, you do get past the model evaluation and everybody's happy with the results. So now it's time for data storytelling. You need to come up with results that you can, produce a narrative that describes in non-technical language this whole process. And for stakeholders that are not data scientists, they need a way to, judge the relative success of this project. And I find that this is like maybe the most challenging stage of the data science process because it is very subjective. It's non-technical. You have to bring down the technology to a very understandable level, and it's almost like you have to put on your MBA hat for a while. Maybe if you have an MBA, that means you're used to thinking about business processes, and you're able to communicate these processes in a viable way for people to understand. So what data storytelling is often about or centered around are these compelling data visualizations that you maybe generated in an earlier stage of the process, these expository plots that I alluded to. Maybe those will be sufficient to communicate the results of the project. But in addition to those, you also have to figure out a way to visualize the results of the machine learning algorithm. Now, you might try to say or to embed like a ROC curve in this data storytelling report, but in my experience, you can often explain that to your blue in the face, and people that just aren't data scientists might not understand that. So you might have to come up with something that is more commonplace, and that's why I said this is a hard part of the project. You really have to think long and hard on how you want to communicate the results, but it is doable. There's a lot of examples online of how to do this, and data storytelling is a big thing right now A lot of people are talking about it because it's so important to get right. The last box in this process is a box that I personally don't engage in my projects, production deployment, because I feel that this is more the job of data engineers. And so in my work, in order to deploy into production with all the work that I just showed you, I will work with one or more data engineers to deploy. And I can advise, I can consult with them on each of these stages, like how to put together a data pipeline and, all the ins and outs of the machine learning algorithms that I use, hyperparameters and things like that. And then we work together to come up with a production solution. And that I feel works out better than trying to, force the issue of does a data scientist also do the work of a data engineer, which I don't believe they do. So in any case, this is my view of the data science process, and I hope the talk has been productive for you and has shed some light into what data scientists do. I love doing all these things, and I have a great time solving problems with data science. So for now, thank you for watching, and come back to see our next Data Science 101 presentation. Thank you.